Lenz's law, this is not a formula on your formula sheet. This is a concept, and you're going to get it in English, and you're just going to have to commit it to memory. But it's going to kind of make sense. It's a consequence of the law of conservation of energy. Consider the following situation. So we're moving a magnet to the right. In fact, we're moving the north pole of a magnet closer to a coil. Will there be an induced current? Don't write this down. Let's just use our imagination. So we have our magnetic field lines going this way. Don't write that in. Will the flux change as I move closer to this coil? Yes. So will there be an induced current? Same answer. Okay. So part A says, will there be an induced current? Yes. Since there is a change in flux. The next question, Chantal, is what direction? Don't write this next bit down. It seems to me there are two possibilities. You could have a current that creates a north pole there and a south pole there because it's a solenoid, or you could have a current that creates a south pole there and a north pole there. This one is a problem because like poles, unlike poles, if this was the current that was created so that there was a south pole there, it would cause this to move even faster, which would increase your change in flux, which would make a bigger current, which would make a bigger south pole, which would cause this to move even faster, which would increase your change in flux, which would make a bigger current, and you'd get free energy. That violates the law of conservation of energy. This would be a system that you just had to tap once, and it would magically give out more energy than it put in. The universe steps in and says, no, the law of conservation of energy cannot be violated. Whatever you try and do, the universe is going to oppose. What would oppose a north pole getting closer to this coil? It's going to put a north pole right there because like poles. Now we can use our right-hand solenoid rule. Hold that solenoid in your right hand. Point your thumb north. Your fingers curl in the direction of the current. You know what? The current is going to be going this way. It's going to be curling up from the bottom, going away from us over the top. It has to be, because if it didn't, you would be getting free energy. It would violate the law of conservation of energy. So what does Lenz's law say? Gibson in English, it says, an induced current will always create a magnetic field, and here's the key word, that opposes the change in flux that created the induced current in the first place. In other words, I'm sorry, but in our universe, you get nothing for free ever, except maybe your mother's love. Maybe. Maybe. Oh, sorry. This also explains the negative in Faraday's law. Remember last lesson I told you there was a negative there. What's the negative telling us? Oh, we got to pause for a second. Hang on. Give me 2 seconds to pause the recording. So the negative here tells us that the induced EMF, the voltage, is created by a current that's creating a magnetic field opposing the magnetic field that created the current in the first place. And so there's going to be a lot of right-hand rule directional questions here using Lenz's law. Let's look at one. Example 1. It says this: a loop is placed in a region of magnetic field that is into the page. The field then changes direction, so it's pointing out of the page. What's the direction of the final induced current? So we look at the final diagram. That's this one here. Jacob, what direction is the magnetic field that's creating the current? What would resist a magnetic field pointing out of the page? What would oppose a magnetic field pointing out of the page? A magnetic field pointing? The coil is going to create a magnetic field into the page. So let's use our right-hand rule. We'll hold the coil in our hand. We'll point our thumb into the page. Do you know what direction the current is going to go in this coil? It's going to go in the clockwise direction. You'll see we often use CW for clockwise and then either CCW or ACW, CCW counterclockwise, ACW anti-clockwise. If the answer key says ACW, you'll know I stole it from a British website when I was stealing the graphics. Yeah, because if it didn't, what you would be getting is free energy. If it created a magnetic field matching the magnetic field coming out of the page, well, now the magnetic field just got stronger, the flux just got bigger, the current just got bigger, the magnetic field just got stronger, the flux. You don't get that. We can't get that. Example 2, the diagram below shows an aluminum ring and the current induced in it. So now they're telling me the direction of the induced current, and it looks like the induced current is that way. Okay. Well, whatever that current is, it was created to oppose what's being done by this magnet. It says the magnet must be A, stationary, moving to the left, moving to the right, or spinning. You know what? It can't be stationary, because if it was stationary, we would have no changing flux, no current. So I know A is wrong. Okay. Pretend you're holding that aluminum ring in your hand like a solenoid. Curl your fingers in the direction of the current. Which side of that ring is north, the left side or the right side? Sorry? So the current that was induced put a north pole right there. That's resisting whatever the magnet is doing. What could the magnet be doing that would cause this coil to put a north pole there? It would be if we were moving the south pole further away, because the south pole, as it moves away, the north pole would be saying, no, 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 I'm going to try and hold on to you. This must be moving to the right. That's the only way that works. That's Lenz's law. Example 3. The before and after pictures I find are the easiest ones, but we'll look at all sorts of variations. It says, will the induced current below flow through the 15 ohm resistor from X to Y or from Y to X? Tony, look at the after diagram. What direction is the magnetic field that's causing the current in the after diagram? What do the dots mean? So this current in this coil was caused by a magnetic field pointing out of the page. It's going to create a magnetic field that will resist that. What will resist out of the page? A magnetic field pointing. Everybody point your right thumbs into the page. Curl your fingers in the direction of the current. And I think I find my fingers are curling this way. Yes? And now if I follow it, follow it, follow it, you know what? It's going from Y to X, not from X to Y. That's actually, if you're ever using a rechargeable device that has a crank to recharge it, here, if you want to turn this for me, you'll find it doesn't turn that easy, and it's not because it needs lubrication. You're feeling Lenz's law. As you're turning it, whatever that system is creating a magnetic field that's creating a current resisting you try and turn it. Turn it faster, you'll feel it resisting more. Now, this is more complicated because it's a spinning magnet, and I'm not going to ask you a spinning magnet question, but if you have any kind of like a rechargeable radio, an emergency radio, or an emergency flashlight, when you turn the crank, that feeling that you feel resisting you, that's Lenz's law. If we're moving the magnet to the left, find the coil's induced north pole and the direction of the induced current. So we look at the pole that's closest to the coil. Yosef, what pole is closest to the coil? What direction is the north pole moving? Is it getting closer or moving away? Which one of those is correct? Is it moving closer or is it moving away? Okay, this coil will create a current that creates a magnetic field that resists a north pole moving away. What are my possibilities? Don't write this down. Would that resist a north pole moving? No, 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 that would push it faster. So what's it going to be? Oh, a south pole is going to be there. Write that down. A north pole is going to be there. And now hold the solenoid in your hand so that your thumb is pointing north. Your fingers curl in the direction of the current. Is the current coming up over the top towards us, or is the current coming from below out of the bottom towards us? Coming up over the top. Current is this way, this way, this way, this way, because of Lenz's law. You get nothing for free. Let's look at a bunch of, first of all, I got to show you a demonstration. This is a really cool demo. I'll pause the video for a second. Sorry for those of you at YouTube. Goes down, look up. I'm going to mute it. Here's a very nice example of Lenz's law. We have a copper plate, which is not magnetic. If you drop it, a big magnet onto it. Magnetic pressure. Watch that here. I don't know whether the North Pole or the South Pole is pointing down, but it induced a current in that copper plate that opposed the magnetic field it was causing. And if it was a South Pole moving down, the South Pole up to resist that. Or, here's a nice big one. I would get this, but this costs about 900 bucks. But there you can see what Adam saw when he put his eye to the copper pipe. It's definitely not in free fall. And in fact, you can even apply a force sideways to it. You can see how it's inducing a current enough that the oppositional force, since forces come in pairs, the pipe feels the force and starts to roll. All examples of Lenz's law. Copper's not magnetic. There's no magnetic fields occurring here, except for those that are created by the induced current temporarily. It says this: determine the direction of the induced current in the loop or coil in the following diagrams using Lenz's law. The arrow indicates which way the loop or magnet is being moved. All right, so we have a magnet going from no magnetic field to increasing magnetic field. So I said magnet. A coil going from no magnetic field to increasing magnetic field pointing which way? What do the X's mean? What would resist increasing into the page? Increasing which way? And so the current that's going to form in the coil is going to be in that direction, which would be counterclockwise. Here, we've moved it from the magnetic field to no magnetic field. So we've gone from, originally it was here, full into the page, to no into the page. That's a decreasing into the page. What would resist decreasing into the page? What's the opposite of decreasing into the page? Increasing into the page. So point your right thumbs into the page. In this situation, the current will be in this direction. Clockwise, which makes sense because these are two opposite situations. We got opposite currents. Similarly, in this next diagram, we're moving into a magnetic field, but which way do these dots mean? Which way is this magnetic field pointing? We have increasing out of the page. What would resist increasing out of the page? You could either think decreasing out of the page or increasing into the page, which is really the same thing. So point your right thumbs into the page. This is going to have a current in this direction. It's going to be clockwise. Compare that, and again, we're having to imagine that originally it was here, and now it's moved out of that magnetic field. That's a decreasing flux. What's decreasing? Decreasing out of the page. What would resist decreasing out of the page? Increasing out of the page, right? So you're going to have a magnetic field, point your right thumbs out of the page. Now the magnetic field in this situation is going to be counterclockwise. Sorry, the current is going to be counterclockwise. Magnetic field out of the page. These four, I find really tough. I find it tougher when the coil is moving. I find it way easier when the magnet is moving. So in this situation, we have a look at the pole that's closest to the coil. We have a south pole getting closer. What would oppose a south pole getting closer? Yeah, going to be a south pole there, a north pole there. Now hold the solenoid in your hand, point your thumb north. My fingers curl, I think, this way, this way, this way, this way, this way. And if I follow it, you know what? It's going through the resistor from right to left. It's going to the left through the resistor, which is probably what I would ask. I'd probably put like an A and a B or an X and a Y and say, is it going from A to B or from B to A or from X to Y or from Y to X? Here, same magnet, but this time the south pole is moving away. What would oppose, Carter, a south pole moving away? If I put a south, don't write this down. If I put a south pole right there, that would oppose this moving away? Ah, that would increase it moving away. That would be free energy. The law of conservation of energy says, nuh-uh. A north pole there, a south pole there. Now I hold the solenoid in my hand with my thumb pointing north. And this time I get the current going this way, this way, this way, this way. Did I do that right, Mr. Duke? Yeah. And so if I follow it, it goes this way. Yeah, now it's going through the resistor from the left side to the right side. What if this magnet was spinning? Well, then you would have a south pole here, then a north pole here, then a south pole here, then a north pole here. This is why it's so much easier to create alternating current. That's what you would get. If your magnet is spinning, if you have something turning a turbine, you're going to get alternating current. You can generate direct current, but it's a pain. Alternating current, way easier. Ooh, here we have a north pole getting closer. Okay. Cormac, what would resist a north pole getting, Cormac, sorry, Alfie, I don't know where that came from. What would resist a north pole getting closer? So you're saying a south pole right there would make this slow down? Ah, a north pole right there would oppose it, would make it slow down. So we're going to end up with a north pole right here, a south pole right here. Now hold the solenoid in your hand, point your thumb north. I'm getting the current going this way, yeah, curling up and over the top away from us, right? Compare that to here. We have a north pole moving away. Hey, that would put a south pole to say, come back. North pole there. And now I have the current going this way, this way, this way. Now I have it going through the resistor from the right side to the left side. So some neat applications. Put your pencils down, look up.
This is my guillotine. It's got a copper blade on it. It's about 4 or 5 millimeters thick, and it weighs, as you can see, on the order of 30 newtons, maybe a little more, but about 30 newtons. Now, that blade, and take this scale up, is free to slide up and down here in these aluminum channels. If I put it up here, let me show you what it can cut. Now, This is actually much better done with a cantaloupe or watermelon, some fruit that'll chop apart with a nice splatter as well, but I don't have that available. Let me show you what it'll do to a soda can. I put this soda can in here and drop this on it. You can see it pretty much just, well, it stays there, slices it through, and it'll go pretty much through a watermelon. Here you can see that can got totally crushed there, and doesn't actually chop it through, but fruit, it goes all the way through. Now, you would obviously not really want to put a part of your body here and then release this, except I can. These are 4 really strong magnets. Now, magnets are not attracted to copper, okay, nor aluminum, so there's no sticking to these pieces of metal. Iron, like this little piece of chain, oh yeah, stick to that and take some force to pull away. But the blade, not so much. Now, if I put them here at the back, so that the blade isn't going to rub against them on the way down, it slides past them. You look from above like I am, you can see there's actually a gap of about 2 or 3 millimeters. But now, it's safe for me to put part of my anatomy through there. Now, I can't reach with my arm and pull this out, but let me put my foot in there for you, okay? And just to show you that I'm not cheating, let's take the shoe off and drop this onto my foot. Ha! Why didn't it chop through my foot? Electromagnetic induction. It's science, guys. That's what's going on here.
Lenz's law. And another really cool application, a levitating barbecue.
Let's switch it on. Let's see what it does.
Through this coil of thick wire, we're about to pass a huge alternating electric current. On top is a 1 kilogram aluminium plate.
So we hear this noise. What's that noise?
It's the vibration of the plate because it's vibrating at 2 times the frequency of this one.
Whoa! Whoa! How does it do that?
So we have an alternating current in a massive solenoid. So the magnetic field will be pointing up, pointing down, pointing up, pointing down. It's inducing currents in this aluminum plate, and those currents are creating magnetic fields that oppose whatever's creating it. So it's going to have all these opposing magnetic fields. It'll hover.
To find out, I've come to the place where it all started, the Royal Institution in London.
This is the key to Faraday's magnetic lab.
We still have Michael Faraday's lab. It was turned into a storeroom for a couple of 100 years, so it was left intact. Now we've restored it to its pristine glory.
It's amazing that lock still works.
From the 1870s onwards, it became a storeroom, which is why it survived, and it survived intact, all the joinery, giant electromagnet, exactly the same as Faraday
So this
left
is
it.
exactly as Faraday would have had.
That's right, yep.
In Faraday's time, it was known that electric current creates a magnetic field, but it remained an open question whether the reverse is possible, if a magnetic field could generate electric current. Faraday answered this question with his most famous apparatus.
Faraday's electromagnetic induction ring, which is this.
In August 1831, Faraday wrapped 2 coils of insulated wire around this iron ring.
But in 1831, you could not go down to your local electrical hardware shop and ask for X hundred meters of insulated wire. You had to insulate the wire as you went, and so as you pushed and pulled the wire out of the ring, you had to insulate it. It takes 10 working days, which is a huge investment of time.
But the investment paid off. When Faraday connected a battery to one of the coils, he saw a brief pulse of current in the other coil. And when he disconnected the battery, he saw a pulse of current in the other direction.
This is Faraday's brilliance. Other scientists had set this same apparatus up, and when they switched it on, they said, I'm not getting any current. Faraday was the one that noticed, wait a minute, right when I switched it on and right when I switched it off, there was a brief spike. Why? Because that's when the magnetic field is going from, the flux is going from 0 to full, or from full to zero. And that's where he was the one that had the aha moment. When is current induced? When there's a changing flux.
He realized that current was induced in the second coil only when the magnetic field through it was changing. And if they hadn't been wrapped on the same ring, Faraday may have noticed that the two coils repel each other when the current is induced, and that's due to the interaction of their magnetic fields. Which brings us back to this. Through the bottom coil, we are passing a huge electric current, 800 amps, which alternates in direction 900 times per second. This ensures there will always be a changing magnetic field above the coil. Instead of a second coil, we're using the aluminium plate, but the principle is the same. The changing magnetic field induces currents in the plate that create an opposing magnetic field, so it levitates.
How awesome is that?
This current is not only good for levitating the plate, it can also make light bulbs glow.
A gift.
Oh, thank you. Oh!
How is it glowing? Because now this aluminum plate is sending out an oscillating magnetic field. See the coil at the bottom of the light bulbs? That coil is experiencing a changing flux, and so current is flowing. This is one way to generate or pass power wirelessly from one object to another. Yeah. I suspect something similar, yeah.
That is cool.
Not too close because it will burn the arms.
Can I put it there?
Yep.
And just as current in a toaster element heats it up, the induced current in the plate dissipates its energy as heat.
Add some water too.
Thank you.
Yeah, to see the temperature.
Check it.
So it's steaming hot. The water is sizzling. Now, why is that? Because it's an alternating current. And so because it's an alternating current, you have electrons basically rubbing on each other, back and forth, back and forth, back and forth. That generates a lot of heat. This, to me, would be the most impressive dinner place setting ever. It hovers, you put a lamp on it, and you can cook on it. Everybody can put their own little dish on there and cook away. It's a levitating barbecue. I mean, all it needs 800
How
amps.
hot this plate is. Oh, that is nuts. Is this your favorite demo?
It's like a flying barbecue or something.
Tell me this is not the best dinner table centerpiece. It levitates, it gives you light, and you can cook on it. And all the while, you're demonstrating Faraday's law of electromagnetic induction.
And Lenz's law. I mean, come on, that's pretty good. What's your homework? Try every question. A couple of, so there's a whole bunch of just directional ones. Number one, I stole this from Britain, so it's ACW is anti-clockwise. That's why CW and ACW. When you get to some of the ones where you're going to be crunching numbers, number 4, number 5, please notice whether they gave you a radius or a diameter, because pi r squared, not pi d squared. That's a hint for number 5. And these are all great questions. Class is yours. I'm going to pause the video.